Hi, I am presenting Conformal Predictive Safety Filter for RL controllers in dynamic environments on behalf of myself, Nora Ayanian, and Lars Lindemann. Learning-based systems are increasingly used in safety-critical applications, often trained online in simulation and deployed across a wide array of applications, such as vehicle navigation. In this paper, we focus on the task of controlling an ego agent X to a goal while avoiding the other agents and their trajectories tau. Learning-based controllers have been shown in recent work to perform well at this task. However, given one of these controllers, there's still uncertainty in whether it will collide with other agents. Here we have an example scenario. The ego agent robot at time t is trying to avoid a bicyclist agent and has a history of observations for that other agent from 0 to t. The ego agent takes an action from its nominal control policy pi and is at risk of colliding with the other agent. We can improve upon the reactive controller by training a trajectory predictor Y for the future trajectories of the other agents. However, there exists uncertainty in these predictions, and quantifying the uncertainty without being overly conservative is difficult. We desire a safety filter pi hat that will avoid the other agents with greater surety without greatly deviating from the original performance. To do so, we propose a safety filter method that is probabilistically safe in the number of collisions, minimizes the difference from the original controller, and is flexible with minimal assumptions and reduced conservatism. Our method follows a couple of steps. First, we train a predictor of the other agent's future trajectories. We see their predicted trajectories here. Second, we use conformal prediction to quantify the uncertainty intervals. The intervals are the shaded regions here. And third, we forward simulate the ego agent's nominal trajectory given the predictions. Here we can see how the ego agent using the nominal controller policy avoids the predicted trajectory, but may collide with the conformal prediction interval. Finally, we learn offline and apply rapidly online the safety filter pi hat, such that it avoids the intervals but differs minimally from the nominal trajectory. You may be wondering, what is conformal prediction? Well, we refer you to our paper and to two other papers here for a more in-depth explanation. But conformal prediction is uncertainty quantification under minimal assumptions, such as no assumption on the distribution of trajectories and no assumptions on our predictor. What it does assume is the availability of data and a given failure probability specified by the user. We want to obtain prediction region C such that the true label or value of Y is contained by C to that specified failure probability. A common example of conformal prediction is demonstrated here, where the prediction sets are broader for an image of an animal it is less sure of labeling than for an image it is confident of its label. Conformal prediction finds a quantile across a calibration data set that satisfies the given failure probability. We use conformal prediction in our work by adapting it for the trajectory predictor and producing intervals around those trajectory locations. Again, given a failure probability, we calculate the nonconformity score or the prediction error across the calibration data set of trajectories such that the lemma holds for a quantile associated with a 1 minus delta probability. This quantile is calculated as the k plus 1 and 1 minus delta smallest nonconformity score. Here's a brief overview of our entire method, and it starts with our system, the environment it operates in around other dynamic agents, our trajectory predictor, and the conformal prediction intervals. These are all combined with the forward simulated nominal control system, and we use them to train our safety filter. We learn this safety filter for H future time steps, hopefully producing a trajectory that is safer across those H future time steps. We learn it such that the future trajectory also deviates minimally from the nominal controller trajectory, yet avoids those conformal prediction intervals. And we assume that this is learned sufficiently offline and can then be applied quickly online for the next time step. We learn the safety filter with a simple network that adjusts the given controller actions. We use 3 data sets for predictor training, conformal prediction calibration, and safety filter training to solve the problem approximately. We test our method in the GIM collision avoidance open source simulator, which has pre-trained RL controllers and has been proven to transfer well to physical robots in mobile navigation, yet still collides in some cases. We run sets of 2, 4, and 6 agents with our data sets composed of 21,000 instances split among training, calibration, and testing with a failure probability of 0.01. We can verify that our conformal prediction is working by looking at the error coverage. We can see the average error here is around 0.2, which is less than 99% of our given safety levels specified by the user, which are both contained by our conformal prediction interval just below 0.8. We can see on the right side that across time steps, the highest error, or the black dot, is contained by the yellow line, our conformal prediction interval at each time step. When our safety filter is paired with the RL controller GA3C and also Orca, we can see that our safety filter minimizes the number of collisions. Fantastic, this is what we wanted. It also deviates minimally in the time to goal and performance from the given controller, and is not overly conservative and makes minimal assumptions. In the bottom left, we compare our method against a Gaussian-based approach that over-approximates the interval in order to capture 100% of the future trajectories, but it increases the time to goal greatly, whereas ours doesn't. To summarize, our conformal predictive safety filter is safer in the number of collisions, efficient with minimal adjustments to the given controller, and flexible by making minimal assumptions and minimizing conservativeness compared to other methods, enabling better and safer performance when deploying learning-based controllers. Thank you for your time.